I think the key thing is that we see nonproliferation as covering two broad areas. One is stopping the spread of nuclear weapons to nations or terrorists. The other is a whole collection of efforts to try to prevent that from happening. And they range from treaties to diplomacy, all the way to military means. If you think of what Israel bombed in Syria, it was an attempt to stop proliferation. And so it's a very broad area with a lot of tools, and in that area, there's a special category which, does anyone not know what nuclear weapon states are? I mean, maybe that's the wrong way to ask the question. Does everyone know what are the nuclear weapon states and the non-nuclear weapon states? Because in our work, we view that non-proliferation includes disarmament efforts when it intersects with non-nuclear weapon states who have sought nuclear weapons. And that includes India, Pakistan, and Israel. Technically, they're non-nuclear weapon states because they didn't test a nuclear weapon by some date in 1968. And then it also includes signatories to the NPT that have sought nuclear weapons. So we bring disarmament into that discussion. And some of the lectures will cover that. In fact, one part of today, I'll look at the South African case. Now, I mentioned this, it's a technical field, and it's very hard to understand it without understanding the technical side of this. And we're going to try to provide some basics on that. And then later courses will get into other topics. And I think one we've decided to do in the winter is we'll do a survey of the Iran nuclear program from a technical point of view to really understand all you need to know about the Iran nuclear program relevant to any agreement that's reached or not reached, all the discussions of the diplomacy and what's what. Now, in this course, we have 10 weeks, and we're going to cover quite a bit, from nuclear explosive materials. We'll get into how reactors operate and plutonium is produced and separated. We'll do a lot on uranium enrichment. We'll touch upon the basics of nuclear weapons development, and how much will just depend on how much time we have. It's one of the more sensitive topics, and one of the ways we deal with it is by avoiding the discussion. But today I'll give a lecture that will touch upon several aspects of nuclear weapons development, but if there's another lecture, will just depend on time. We'll also cover some specialized area, illicit nuclear commodity procurements, how countries get the wherewithal to build nuclear weapons. These countries that we study don't have great industrial bases, so they have to go out and buy a considerable amount to put together the facilities to make nuclear explosive materials. And then we'll also spend time trying to use commercial satellite imagery as applied to nonproliferation. Now, it's often said that it's easy to build a nuclear weapon. I mean, separate from getting the nuclear explosive material, but if you go to the internet, you talk to people, they'll say it's an easy thing to do. It actually, if you look at countries building them, India, Pakistan, Iran, be careful on Iran, but we will talk about the information about Iran's nuclear weapons program. At least we'll touch upon that. It's IA information, and it's available. But they have problems. It's not as easy to do, and there's a lot of challenges, and even to build a crude nuclear explosive. And I'll admit it's not as hard as building a uranium enrichment plant to produce highly enriched uranium, or a reactor and chemical processing plant to create separated plutonium, but it has its own challenges. And if you want to put that nuclear weapon on a delivery system, there's new challenges. It's a military system. It has to meet criteria of reliability, safety, security, and at military standards. And that can be extremely challenging. If you want to put it on a ballistic missile, you have to worry about miniaturizing it. and that creates additional problems that have to be overcome. Now, all the states that go about this will overcome these problems, but how long it takes depends on their skills and also the outside help. In many cases, it's been the outside help that has been critical to speeding up the process. And also, one thing I want to emphasize is you have to get the nuclear explosive material, you have to learn how to, we call it, weaponize it. Those things tend to happen in parallel. It's not as if the state, okay, now we're going to concentrate on a way to get plutonium, and then they get it and they think, oh, now we need to think about how to make a weapon. They typically run in parallel. And so sometimes the state gets the fissile material, and it doesn't take them that long to be able to weaponize it. And also, there's different ways of weaponizing. I mean, if you think through the Iranian problem, and when, in a sense, if they broke out and either secretly or overtly got highly enriched uranium in sufficient quantity for a bomb, what can they do with it? Well, they could build a weapon that we don't even know about in some period of time. And that weapon may never be intended for delivery except maybe in some kind of odd emergency by ship or truck. But it could end up being a way to say to the outside world, if you invade us, we'll use it. Well, how would they use it? In a sense, it would be like an Iranian IED would be a nuclear weapon. And so if anyone invaded them, then they would just have to emplace these nuclear weapons where the troops come through and then detonate them. And so even early after they would get, or only when they could make a crude weapon, they would actually create some kind of deterrence against a military invasion. I mean, you could still hit them with aircraft, but it's not clear how effective that would be. But again, they're not going to stop there, and they probably think of other types of delivery vehicles, and they would ultimately think of putting it on a ballistic missile, and that could very well be challenging. There's nothing surprising about the development of a nuclear weapon. If you're going to do it, you're going to start with a simple design. Unless someone hands you a design of an advanced weapon and the help to master it. Getting a detailed design isn't going to be enough typically in this area. You're going to need additional, kind of in a sense, human help. And but typically the pattern has been to start simple and then work from there. And most of what we study are crude fission weapons of two types, implosion type and gun type. And the implosion type is, yeah, the slide's wrong. Yeah, we'll have to correct this. It should be where the former is usually considered more difficult to master. And then as programs develop, they'll get into more advanced weapons. We won't talk about it today, but hopefully later, boosted weapons. I mean, you all know what an H-bomb is. So I mean, that would be a goal. I mean, we worry India's building H-bombs now. We worry, we have evidence that North Korea is working to separate a thermonuclear material, tritium, from a certain process that we know it's working on. And so we're worried that North Korea is exploring more advanced nuclear weapons designs. Now here's a very crude schematic of implosion design. And the idea of implosion design is based on the fact that if you want to make a nuclear weapon, you're going to have something go what's called supercritical, which I'll talk about next week when I talk about nuclear explosive material. But here in a practical way, what you have to do is just find a way to take a piece of metal, could be just some X kilograms of plutonium or weapon-grade uranium, and squeeze it. So it could actually change in diameter by a centimeter. So think about that. How do you take a piece of metal that you could hold in your hand and squeeze it by a centimeter? I mean, the only way to really do that particularly decades ago, was to use high explosives. But the trouble is, it's very hard to get that explosive shock wave to compress this sphere so it doesn't just shoot out one side. Any asymmetry in the explosion is going to push it out on one side, and then you don't get the compression. So it's really an art to figure out how to compress this thing uniformly so that you actually get this shrinkage in diameter, which causes this increase in density, and that's what makes it supercritical. And so you're aiming, in an ideal world, to double the density through this shrinkage of the nuclear explosive material. And this diagram on the left shows it before, and then on the right shows the mass smaller. Yeah, the next slide it's from the Iraqi full, final, and complete declaration from the 80s, and just shows a little more detail of an implosion system. It's unclassified, but it just adds a little more detail where you need some fast-acting electronics, and in this case they were using a spark gap. Well, I won't get into that at this lecture, but in order to make this thing compress spherically, the high explosives have to be set off around this sphere of high explosive very precisely. And so you need a system to essentially send an electrical signal that then gets transmitted to points on the sphere essentially simultaneously. And then that creates if the high explosives are done right, it creates a spherical shock wave. But I'll leave that to you to look at if you're interested. Here's just a picture. This is either Trinity or Nagasaki, I'm not sure, but it's an old US design, very large. You can see the shaped charges. There's a core. It's not the plutonium. I mean, the core has several things in it, and we'll talk about that another time. This is from an Iraqi declaration showing their attempt to thinking through in a very primitive way how you would mount a warhead inside a ballistic missile reentry vehicle. The other type is a gun type, and this one is conceptually a lot simpler. You can, if you have enough mass of nuclear explosive material, if you can assemble it together, it'll be supercritical. And a rule of thumb is if you have twice, I talked about doubling the density, well, if you have twice the amount of material that's enough to make it go critical, which is have a self-sustaining chain reaction. Again, I'll cover this next week. But if you double the amount of what causes criticality, then that'll be supercritical. And so there's some problems that require you to do this quickly. And so the idea was get a naval gun, cut it down, put most of in this case, they put half of the highly enriched uranium at one end fixed, and then shoot the other end down at it. And when they combined, you'll have enough for a nuclear explosion. And that was Hiroshima, essentially. And let me just summarize what I've been talking about on the nuclear explosive material. Again, I'll come back to that. And actually I'll add something else. If you're working on an implosion system, you can use anything. Highly enriched uranium, plutonium, there's a material called, as you'll see in your readings, neptunium. It's neptunium-237, and that'll work in implosion. But if you go to gun type, not everything will work. Plutonium won't work. You can't make a gun type device out of plutonium. And so, but you can with highly enriched uranium and neptunium. And a lot of it is, if you look at the half-life, which again, but half-life is just the time where half the elements have gone through radioactive decay and changed. So if you had this amount of plutonium after its half-life, you'd have half as much. The longer the half-life, the better it is for a gun type. So neptunium has an extremely long half-life, and so does highly enriched uranium. Plutonium's isn't that long. I mentioned that gun types, you're going to have twice the amount needed for a critical mass. So gun types typically use a lot of material. And so if you had we know this from the South African weapons people, their design had about 55 kilograms of 80 or 90% enriched uranium, and later you learn weapon grade uranium is 90%. That contrasts to a Chinese implosion design using weapon grade uranium that needed 25 kilograms. And it was also partially miniaturized for deployment or delivery by a warhead. And we know this it was the design given to Pakistan in the early 80s, which A.Q. Khan was then selling off later, and so the specifications of the design are known precisely in the public domain. So a rule of thumb is that the implosion system can get by with half of the fissile material. So if you're a country struggling to make the nuclear explosive material, then you want implosion. And that explains why the data says Iran, even though it's could use weapon grade uranium in their theoretical work, they wanted implosion because they felt it would just take so much longer to get enough for a gun type. And so I don't think there's any evidence they've worked on gun type in the past, but there's evidence they worked on implosion. South Africa felt it had a lot, felt it could make what it needed, and it stuck with gun type, even though it investigated implosion. And the Iraqis, in their thinking, they were seeking they were really worried about enough highly enriched uranium. They had initially a kind of an old-fashioned enrichment method based on what are called calutrons, and they were trying to design a weapon, at least on paper, that would only have 15 kilograms of weapon-grade uranium. Is talk a little bit about, kind of give a flavor why it's hard to build a nuclear weapon. And if you're going to build it, you're going to have to test it. And I don't mean a full-scale underground test like what they used to do in Nevada or out in the Pacific. I mean, you need to test the components, the subsystems. I talked about the high explosives. You have to do all kinds of experiments to design the high explosive components, the shaped charge. You're going to be doing an immense number of experiments to understand the pressures and temperatures that are experienced when you compress this core. There's all kinds of experiments that are done. And then you also have to learn how to fire this system to get it to actually work, and not just, one side fires, the other doesn't, and the little core just dribbles out the side. Now in that, what people have learned is that you don't need to conduct a full-scale nuclear test to develop a nuclear weapon. That it's simply not true that if you wanted an implosion system or a gun type, you would have to have a full-scale underground test. And in fact, I remember I interviewed I guess he was the father of the Iraqi nuclear weapons program, a guy named Jafar, back in the 90s, and his attitude was that it sure wasn't the first devices we would ever test with if they were able to have built them. And the idea would be they would test to demonstrate and then to improve their capabilities. And that's what we think North Korea is doing. It didn't actually, it could have gotten by without a test. It had a design, but the test improves its design and makes a point that's hard to miss. And in the case of Pakistan, they went through, we call it a certification process. I mentioned they had a nuclear weapons design from China, and they went through a certification test to prove to the leadership that it would work. But it's not easy to do. I mean, it takes some real work, and there's a lot of difficulties that have to be overcome. You can also improve designs. I mean, we saw that in the case of Pakistan. They talked about it. It's from their weapons people after their 98 test, where they went from the time they got the design from China to when they tested in 98, they went through six advancements in weapons design. Again, nothing like what the U.S. had done, even in 3 years of testing after 45, because testing will allow you to expand your capabilities dramatically. But they were able to advance their design. And some of that was seen in the information seized during the Khan investigations. There were some advanced nuclear weapons component designs that Khan had transferred out of Pakistan and were found on computers in Switzerland in one of their cohorts that were involved in their proliferation schemes. But if you don't do full-scale tests, you're going to have uncertainties. One of the biggest is what is the yield, that you can't. It's very hard to predict the yield you'll get without a test. So in the case of South Africa, well, it wasn't quite as big as this, 5 or 20 kilotons, but it could easily be by a factor of 2. They would have very sophisticated theoretical calculations, but they still, without data, they would have some uncertainty. Now with implosion design, you're also going to have uncertainties on the reliability. I mean, it is a very complicated system compared to gun type, and until you test it, you're going to have, you don't know how well it's going to work. It just is a basic issue of, you turn a switch on, with a light bulb, it's going to work, every time until the light bulb burns out. But on a system like this, some of the times it's just going to fail. And so how often is that? Is it 1 out of 2 times? And Pakistan and North Korea got a shock when it did test in '06 that its yield was a lot less than it expected. It looked like it had misfired, maybe pre-initiated. Also, without testing, you're not going to go too far down the line of nuclear weapons types. I mean, I mentioned the word boosting. Even before that, you go from a solid sphere to a shell system, because again, you're trying to build momentum at the critical moment. And so, if a solid sphere compressed in diameter, it's a lot harder to do that than taking a shell that then is pushed and then comes together in a spherical shape. So but that's a tricky thing to do. And you need a test to do that, to test your methods. Now, a gun type has some advantages. That there's an experiment you can do that tells you a lot about how well it's going to work, and it can substitute for a full-scale nuclear test. I mean, again, an example would be Hiroshima. Hiroshima was never tested underground before it was dropped. Trinity, they did test. I shouldn't say underground. They never. I'm sorry. Yeah, but they. It was an above-ground test in Trinity, and but there was no need to test the gun-type device. And the terms in the Manhattan Project is they called it, the experiment was called tickling the tail of the dragon. And what it is it's a machine, and it's extremely dangerous to do. I mean, technically it's called a pulsed fission reactor. But what you're really doing is taking, in the simplified version, you're taking a slug or a piece of highly enriched uranium or weapon-grade uranium and sliding it down a wire or a track through an annulus of weapon-grade uranium. And so when it goes through, it's critical and you hope it continues, that it doesn't get stuck. And that's actually the danger, is if something happens where it gets stuck and it's critical, then you have this essentially a reactor, unshielded reactor that is operational. But if you measure what's going on when it goes critical, you learn a lot about how your bomb will ultimately work. And the U.S. conducted those experiments, and the documents have been declassified on the U.S. experiments on tickling the dragon's tail. And in South Africa, just to give some examples, this is the building where they did it in South Africa. It's called Building 5000, and they did it in 1978. In fact, as soon as they got enough, and this was 80% enriched uranium. They couldn't make 90% at that time. The enrichment process wasn't working well enough. But as soon as they got enough 80%, and what they did is they had a design that required 55 kilograms. That's how much they got. but with 80%, they would get less of an explosive yield than 90%. But it was exactly the same design. And so they then took it to there and did this experiment. And then that's the one test they did in this reactor. They never operated it after that. And again, just to bring in the satellite imagery, it's a very nondescript building. I mean, I met it just by coincidence. Our daughters went to the same nursery school or school. I met one of the major participants in this program, and he had not intended to be a spy in the 70s and early 80s, but he didn't want to work in the nuclear weapons program. And he had been at one of our Ivy League schools as a PhD or postdoc, and he just wasn't comfortable in the weapons program. He had other responsibilities at the nuclear site that didn't involve weapons, and he just left one day, just left South Africa, which turns out to be illegal under the South African classification system. So they put out to Interpol a red notice and accused him of being a drug dealer. And he was in the United States by that time, and he decided that he didn't feel like being arrested as a drug dealer, so he approached our government and revealed a lot about this program in the 70s, that it wasn't that well known. And the one of would have been this, and this facility was actually, if it was working, there was no one there, and that this is the building 5000. The control building was about 3/4 of a mile away in what is called building 5100, and it had a lot of other functions, but in it was the control room for that reactor, and that this I don't know if you can see it here. I'm not sure this helps, but what this is just a Google Earth image of the building 5000 and building 5100. Building 5000 is in a valley, so that if you're at building 5000, you look around, all you see is the hills, and so that the natural way to protect was to use the hillside. So if this thing went bad, then they would have the geology or geography to protect them. But once they did the test, they had much greater confidence. And it's also, this is an example where we'll start to hide their capabilities. And this was a first attempt. I mean, in this case, in a sense, defector. He wasn't really, but a defector reveals the program in great detail. But it's a program that gets revealed too because it's so close to this Pelindaba nuclear site. This is the South Africans' main nuclear site where they have civil activities. There's a U.S. supplied reactor right there. U.S. people go there, others go there, and then down the hillside, down in a valley, there's a river down here, the Crocodile River. Then they put these secret nuclear weapons development sites. I remember talking to them that they weren't that convinced it would work because they were also developing implosion weapons, at least studying implosion weapons. And well, what do? You blow off high explosives. So if you're up here visiting and you hear explosions down in the valley, I mean, you will probably tell your government if you're paying attention to these issues, to take a closer look. And so this idea of putting things adjacent to a declared nuclear site isn't the most effective way to do it. I mentioned how it's difficult to build an implosion system. And typically, a country that's going to do it is going to be thinking about a full-scale test. And so probably the best example is Pakistan. Even though they had a Chinese design, they developed a certification program to say it would work without full-scale testing. They started building a nuclear test site in case they wanted to test. And in '98, after India tested, Pakistan was able to test within a few weeks and conduct 5 tests simultaneously. I think it was 5. and then a day or two later, they detonated another one at another site. And so you look for these test sites if you think the country is following the implosion route. And here's the mountain where the Pakistanis detonated their device. And there's a video. Did we ever put the video on our website?
Yes.
Okay, yeah, so you can, this wasn't publicly known, even until after the test. In fact, even, I'm forgetting some of the chronology, it wasn't known after the test. But we did a study to find this location.
Yeah.
And one of the things we did was we wanted to get the video, and we called the Pakistani TV station and asked for it, and they sent us this incredibly great, it was called beta quality video, and it arrived in a burlap bag one day from Pakistan, and it was just remarkable imagery to understand the test. And you could actually look at it and zero in on the facilities there and how they'd actually camouflaged. So from above, this looked like a village, but it was actually bunkers and instrumentation locations where that were critical to doing the test. But again, I think this stuff is on our website. And I apologize, I forget these things. It's been quite a long time, and I'm getting old and forgetful, so. The next section I wanted to cover was on miniaturization. I mean, it comes up in the debates all the time. If you follow North Korea, a lot of the debate is, can they put a warhead on a missile or not? And there's a complication to the debate, can the missile reach America, or when will it reach America? But, and that's a more profound debate on how capable they are with ballistic missiles, but there's been this debate over, can they miniaturize and actually put it on a shorter range missile, which would be called the no-dawn. So, and it really follows that most states, when they think about building a nuclear weapon, are going to have typical delivery systems that they feel they can control. And it can change with time. So in Pakistan, their delivery system of choice was the F-16, and then they bought a missile system from North Korea, the Gauri, and so by the late 90s, they switched to ballistic missile delivery. And again, it's not, it's a logical progression. A lot of this is all just a logical reasoning that you want to be able to get through to your enemy's developing better defenses, attack aircraft such as the F-16 can work, but they can be shot down, and India gets more and more capable systems. Ballistic missile is very hard to shoot down, so it's very typical. Now, what I'd like to do is cover the South African case in a little more detail, and also show how they think about it, or how they thought about it. In 1977, the Russians discovered a secret South African nuclear test site. And I mentioned, they had a gun type. In 1977, they didn't have enough weapon or highly enriched uranium for a bomb. That was in 78 when they did Tickling the Tail of the Dragon. They didn't even need a nuclear test site. But nonetheless, they built it because of this idea of building a lot of things in parallel. And in 1977, they decided, why don't we just have a full-up mock-up of a nuclear explosion? And so they designed a mock-up. They started putting everything out there, and the Russians detected it, and then told the Americans, and just an alarm went off worldwide that South Africa was getting ready to test a nuclear weapon. And it led to UN Security Council sanctions on South Africa. They had been in the works for a while, but the nuclear aspect tipped them into passing, and a military embargo was placed on South Africa in the fall of '77. this is a schematic, and this was done by, he was in the South African program, a guy named Andre Bays. So Andre Bays is in the South African program. He started in the early 70s working on the development of a gun-type device, and he's been one of the more open people once they abandoned their program. And the kind of big, long, cylindrical thing on the left is the package they were going to put down this hole. And it would have the bomb itself and then instrumentation, because there was going to be scientific experiments. And for a lot of the people in the program, it was a peaceful nuclear explosive. They were going to learn all about nuclear explosions and how, and then could you apply them to build a harbor or do mines. In the back of the mine, you know, it could be a weapon too. But they're as this colleague of mine represents, they weren't all looking to build nuclear weapons to deliver against the frontline states, as they were called. It was a very hectic situation down there with, again, you may not remember, there were 50,000 Cuban troops in Angola by this time. There was an active war going on, so you had, in a sense, Russia surrogates on one side, and you had South Africa on the other, where the U.S. was behind it, but was losing interest because of apartheid government, the apartheid policies. But even with that, a lot of these people were not in the program, were not that enthusiastic about it. But when they were confronted with the public condemnation in this and the Security Council resolution, they made a decision. They said, look, we're gonna go down the route of nuclear weapons because we've been put in a corner. They are putting sanctions on us, and those will stay until apartheid's gone. They've started making a demand that South Africa sign the Nonproliferation Treaty, but if they even signed it, the sanctions wouldn't disappear because of apartheid. And so this is an apartheid regime, so it basically said, look, why not build nuclear weapons? Because for us to agree to these conditions mean we'd have to end our regime as they envisioned it. In '77, the apartheid regime was very strong, and there wasn't a lot of dissent within it. So they decided from one day to the next that they're going to miniaturize, which means they're thinking of it as a weapon. And so when they designed a P&E, in fact, their first device was a P&E, well, they call it P&E, it was a nuclear explosive device designed to go down a shaft. It had been reduced in size from here to there. And the design itself was about half as big. The warhead itself, or the nuclear explosive itself, was about half as big. And it could be deployed quickly, which means if they were going to test it, it was to send a political signal. And they evolved a very elaborate, kind of convoluted nuclear strategy, which was they knew they couldn't take on the Soviet Union. They viewed that the Soviet Union had nuclear weapons on ships offshore. They were worried that if, with 50,000 Cuban troops, Russian support, that they could lose the war. And then they would use this nuclear weapon. They called it back to the wall strategy, that they could use it to not deter the attack, but force the United States to help them, to step in and confront the Soviet-inspired advance. And throughout their program, that was the basic motivation. Now, stepping back a little bit, talk about miniaturization in general, and then I'll come back to South Africa. The states have gone about the miniaturization differently and with different speeds. In China, after their first test in '64, 2 years later they were able to miniaturize for a missile. In fact, shot the missile across China, detonated it above the Lop Nor test site, which also shows you the safety considerations given to these things back then. And but again, in 2 years they were able to miniaturize for a warhead, and that was a design given to Pakistan, and we think probably ended up in North Korea too at some point. And just to give you some sense of these dimensions, that design is about 70 to 90 centimeters in diameter. And in comparison, this Iraqi design that they were working on with 15 kilograms was about 120 centimeters across. And when they launched a crash program in 90 after their invasion of Kuwait, they were trying to get it down to about 80 to 90 centimeters, and failed by the time the war started in early 91. Now, in the case of Iran, they're using a derivative of the North Korean missile, but the warhead the reentry vehicle's changed. Because again, the Gauri is North Korean, the Shahid 3 is ultimately a North Korean design, but the reentry vehicle's changed, and they need a smaller warhead. And the warhead the IA thinks Iran was working on in 2003 was about 55 centimeters in diameter. And so the IA isn't claiming they succeeded by any means, but it was a very small design that Iran was working on. And that's what a lot of these allegations are attempts to get Iran to explain away this pretty solid intelligence information. But again, it shows that if it's true, that long before Iran could have thought of producing weapon-grade uranium, it was designing a warhead to fit on its principal delivery system, the Shahid 3, and taking the steps necessary to do that. South Africa didn't have the greatest military aircraft. They're under a military embargo. They're largely depending on aircraft they bought early. They had something from the British called a Buccaneer bomber, and that became their nuclear delivery aircraft. It had been so for the British, and so they had to think through how do you develop a system for this, a fairly old aircraft that's not going to penetrate Soviet air defenses that were in place, or were being put in place in the frontline states like Angola. And so what do you do? So what they did was they decided to develop a standoff weapon and put a nuclear weapon on that. And here's a picture of it. It's called the Raptor 1 or H-2 glide bomb. And it was developed for conventional use. It actually has video guidance, so it can relay back pictures to the commanding aircraft that's fired it, and then it can be directed at a target, and they demonstrated it in a battle and destroyed a bridge with it in Angola. But underneath that, it was their primary delivery vehicle for nuclear weapons. And the way it looks when you put it on the design of this weapon, it was about 60 centimeters in diameter and 1 meter in length. And it looked like a canister that would then fit into this glide bomb. And again, it was very sophisticated, went through a tremendous amount of testing. It was like a Cadillac model of a gun-type device. I mean, that's the way people have described it. For example, people in the IA who investigated the program in great detail. And again, no advancements in we call it the physics package, the core. You know, they didn't use more sophisticated techniques to assemble the highly enriched uranium. The only thing they did that was unexpected was they didn't have a neutron initiator. I don't know all the reasons why, but if you don't have a neutron initiator on a gun-type device, you risk that this plug is coming down the barrel, like a naval gun, and it hits the fissile material, the highly enriched uranium at the end, and it just keeps going. And so it is like a pulsed reactor, but it's destroying everything as it moves through. So what you have to do is design it normally with a neutron initiator, is that once it's assembled, the neutrons will be produced from a neutron initiator, and that'll start a chain reaction. And otherwise, it'll blow through the back of the bomb. It'll just keep going. But if it initiates, the nuclear explosion will happen so quickly that explosion will happen before it can hit the back. But in the South African case, they didn't want a neutron initiator. So they had to design it so that the plug would actually be caught and not bounce back in the end, and that it would sit there. And there's a mistake in what I gave you in the South African study. I think it talks about in microseconds, a neutron from outer space will set off the chain reaction. It's actually it's milliseconds, if that matters to you. But it's the for some, we should correct that mistake. But so they designed it so it would, this plug fired from essentially like a naval gun is caught at the end, and then a neutron produced in outer space will start the chain reaction. And it avoided having to build this very complicated neutron initiator, which at the time typically required renewal every year. And so they wanted a design that didn't require that. And the homework assignment is, how do you keep it from bouncing back? Because if it hits, it's not going to just stop. I mean, there's got to be a massive end. But how do you stop it from bouncing back? So that's your homework assignment. And here's the Buccaneer bomber. It's a little hard to see this, but the two red-tipped objects are the H2. So the wings fold in, and it's in a tube that can be fired by the plane. And then in a nuclear strike mode, the outer pylons would have a control pod for the nuclear weapons and an electronic warfare pod. And the idea of it was to, again, this is for a later model, but the idea is you can fire it in a standoff mode. It has a range of 60 kilometers. And it has the ability to go straight and then to go down rapidly to target. And you can be controlling it as it goes along and getting information back from the glide bomb. But I'll leave this. When you get the slides, you can take a closer look at it if you're interested. But it worked for them. By the end of the program, they had also worked out a deal with Israel where they were acquiring a ballistic missile from Israel. And just a little, I don't know if you follow what Congress does on sanctions with Iran. In a very real way, Israel was like Iran to Congress in the 1980s. And they took tremendous actions to try to block Israel from being able to provide the apartheid regime with armaments, in particular with ballistic missiles. They failed. Israel did provide the missiles, and South Africa was building them. And by the late 80s, they were building up a program to make the warhead for the ballistic missile. But they hadn't decided would it be a gun type or an implosion type. And they told me, I've been down there and talked to many of them, and they told me they favored a gun type. But they were facing an engineering problem, which is, I said they want to make it secure against unauthorized use. Well, one of the things you don't want to happen with a gun type device is it's a tube with highly enriched uranium in both ends. What if you tip it up and it just slides down? So again, it won't be a nuclear explosion, more than likely with that amount, but it's going to be a critical reaction. So how do you keep the material from going all the way down? And again, I won't make this a homework assignment, but the solution for South Africa is you have this tube and you cock it so that you split it in half and then you twist it so that you have overlapping edges, and so if it goes down, it strikes the edge of the bottom tube and can't go any further. But if you're building a ballistic missile warhead, that's a problem because you want to have everything symmetrical in a missile, because you don't want an off center of the weight, because it can cause the reentry vehicle to act funny. And so how do you build a safety device for the gun type? And they hadn't worked that out by the time of the end of the program. But they were also not sure with their standards that they could build an implosion type weapon that would satisfy all the criteria of safety. that were necessary to have an implosion system. Because again, it's high explosive, it can go off accidentally, and then you could, in some designs, have a small-scale nuclear explosion. So you have to worry about the safety of the implosion system.